Yeah, just remembering to record the meeting. So what is resistance? Yep. Anyone else got any definitions of what resistance is? That's an interesting one. Cool. So if we look here at this blue line, so this is what we're going to use as our reference for resistance tonight, this blue line. So the physical opposition to current flow in a circuit based on the material structure. So metals like copper, they resist current less than others due to free flowing electrons. So we look at copper on the periodic table, it has more, it has slightly less than a half full valence shell, so they're quite loose. Whereas if something has more of a packed outer valence shell, it's harder for those electrons to be broken loose by the current flow. So in DC circuits, current flow is one in constant direction. This resistance fully governs how current can flow. But in AC circuits, resistance still matters because current, even though it alternates, must still pass through this resistive material. So going back to the electrons moving, so current flow is a result of us putting pressure on those atoms, so the copper atoms, and forcing the electrons free. So we have to actually use that voltage to create current. So there's no current flow without voltage, and there is no current flow without a complete loop. So that's something to remember going forward in terms of the atomic theory side. Does anyone have any questions over this so far before we move on to the next topic? Okay, so the next topic we're going to talk about is reactance. Cool. So does anyone have any idea of what we're talking about when it comes to reactance? Has anyone heard that term before? All good. You never know what people have studied before or what people know. So when we talk about reactance, so imagine water flowing through a pipe and there's a turbine in the middle. So at first, when the water tries to start flowing, the turbine resists motion, so it doesn't want to spin immediately. But once up to speed, though, it provides a little resistance to the flow. This is what happens when we pass DC through an inductor. Yep, so Troy already got the nail on the head. So due to inductance, but things are different for AC. So imagine that same flow of water is constantly going back and forth, pushing the turbine from both directions. The turbine would never get a chance to get up to speed and would constantly be opposing the flow of the water. So it's similar to what happens when we pass current flow through an inductor or a coil of wire in an AC circuit. So this repeated reversal causes that turbine to keep being pushed back and forth, acting like a form of resistance, but it's not resistance from frictional material. It's due to that changing magnetic field created by the inductor when current flows back and forth to it. So this opposition is called reactance. So as that water pushes into the turbine initially, there's some of that water gets into the turbine, but then as we try and push it the other way, there's already still that water inside the turbine that we have to push against. So think of it like we've added extra weight in the form of magnetic inductance. So that way we've got to overcome that extra oomph again. So that's what we call reactance. When you guys get into next year, you will learn about both capacitive and inductive reactance. So reactance occurs because of coils or inductors and capacitors, which is called capacitance. But you guys don't need to know about that just yet. It's what you'll cover over in AC theory next year. But we just want to cover over impedance now on reactance because it is an important part of testing, as we'll cover over a bit later. Cool, so some keynotes. So current is like flowing water through a turbine. First, the turbine resists the motion. It doesn't want to spin immediately. Once up to speed, though, it provides little resistance. This is what happens with DC through an inductor. But AC is different. Flow is constantly going back and forth, pushing on the turbine from both directions. The turbine would never get up to speed and would constantly oppose the flow of current. That's similar to what happens when current flows through an inductor in an AC circuit. So I'll just wait a little bit for you guys to either screenshot that or take the notes down, because that is stuff you will need to, that will come handy when you go to revise for the capstone in a few weeks. Okay, cool. So the next part. So this repeated reversal causes the turbine to keep pushing back, acting like a form of resistance. But because it's not friction or the material's resistance, it's because of the changing magnetic field created by the inductor when current flows back and forth through it. It's called reactance. So it's like a turbine always being reset. It's trying to spin up, but every half cycle, the AC current is forced to spin the other way. Constant pushback is what we call our inductive reactance. So the pushback opposes the change in current, not the flow of current itself. And that's why inductors resist AC but not steady DC. So it's opposing the change, not the actual current itself. So we don't need to calculate reactance at this stage. We'll talk about that in year 2. It'll be introduced in a later lesson, but we will, for the next few questions and the questions you get in your capstone, you'll be given the reactance. And we won't talk about, if any of you know anything about power factor correction, that is something we'll cover in year 2 as well. So if we think back, go back to our line representing our resistance. So move this down. So this is our resistance. And then at about 90 degrees, we have our reactance. So this is what we will deal with a little bit later. So, and reactance create impedance. Cool. So impedance is the total opposition to current flow in an AC circuit, combining two distinct forms of opposition, resistance and reactance. So resistance is the opposition caused by the physical properties of the conductor. It's constant and affects both AC and DC equally. It results from electrons colliding with atoms in the material as they flow. It converts some of the electrical energy into wasted heat. But reactance, on the other hand, only exists in AC circuits and comes from components like inductors and capacitors. In the case of inductive reactance, which we'll focus on this lesson, the opposition arises from the changing magnetic field around the coil when alternating current flows. So the changing field generates that pushback we were talking about, not because of the material, but because of that electromagnetic effect, like we were studying with magnetism. So unlike resistance, reactance doesn't dissipate energy as heat. It temporarily stores and returns energy to the circuit. So it kind of acts like a mini battery, which is what capacitors are usually compared to, again, next year. But you just need to be aware that that is what they do and how they act. So reactance only exists in AC circuits, inductors, capacitors, magnetic field, pushback, and unlike resistance, reactance doesn't dissipate any energy as heat. Oh, sorry guys, I don't know what's going on. Go away. Yeah, that's how impedance works. Yeah, cool. But now we'll look at how we calculate it. Cool. So resistance and reactance cannot be simply added together because they oppose current in fundamentally different ways. So we use the Pythagoras theorem to combine them into one value. So who remembers what the Pythagoras theorem is? So most of you got it. So yeah, because we think of it as a vector summed rather than how they were adding together, we have to use our Pythagoras theorem of z equals r squared plus x squared. So yeah, sorry. So yeah, in this formula, resistance is treated as one side of a right angle triangle, and reactance is the other. The resultant hypotenuse is the overall impedance of the circuit. So while we draw reactance at 90 degrees and resistance in this model, the reason for the perpendicular relationship. So yeah, this is the way it works. So yeah, we have our hypotenuse there. Um, yeah, so the impedance is the total opposition to current flow, combining both resistance and reactance. But again, they interact with the current flow in different ways, so we can't just add them together. So we use this in the when we do the mathematical equation. Cool. So real world application. So question. So we go back. So resistance is R. So that was always the what we used for it, and reactance being X. Um, so yeah, we can't use R for impedance because it already stands for resistance. Yeah. I'm not 100% sure why we decided on Z, but we have to use the Z because R was already taken for resistance, and because that way we know. I believe it stems from England because you'll always hear English sparkies talk about their ZS and their ZEs. But whenever we talk about Z, we're always talking about impedance. So you just got to remember when you'll be given a formula wheel at some point for your exam, and you just got to remember that Z is your impedance. So whenever you're using doing a calculation for AC circuits, we need to be using the impedance rather than resistance. Sometimes you'll be given the resistance and how big a capacitor is, or how the rating of an inductor, and then you will have to figure out the impedance and reactance from there. I could show you some of the questions that we get in the year 3 stuff, but for now, we just need to focus on the fact that now that we're starting to talk about AC, resistance is R, reactance is X, and impedance is Z. Um, I have to do some digging into why it's Z. I'm sure there's a history lesson in there. Yeah, I agree, Tim. We should have just used like some Greek letters. Maybe it does stand for. No, there's no Z in Greek. Yep. So Z equals the square root of R squared plus X squared. R squared being the bottom of our uh, Pythagoras triangle, and X squared being the 90-degree side, or our. If we're using the angle at the base of the hypotenuse and the flat, then it's our opposite side. And those, if anyone remembers, so you guys, before you get into year two, will probably want to restudy back on your Pythagoras theorem for and your trigonometry for your SOHCAHTOA, sine, cosine, and tangent, because they do come in handy as you get into year two and year three, because there's a lot of triangles. Cool. So who can think of some real world applications for impedance? Yeah, so most of you guys got it. Yeah, so the most common thing we use impedance for, or the thing we test for, is loop impedance. We also use it a little bit when we do power factor correction, like Sean said, which again you'll cover off in year two. That's mostly to do with motors and transformers. You'll learn about how we can add capacitors, which have the opposite reactive effect as an inductor to increase the power factor of your transformers or your motors. Which is why another way we can use capacitors is for single phase motors. Again, you guys will learn this next year when you talk about motors. Cool. So our Earth loop impedance testing. So EFLI is a real use of impedance. So it measures the total opposition in the fault current path during an earth fault. So we call it earth loop impedance because of the transformer windings, which are inductive by nature and oppose the fault current through the reactance, not just resistance. The opposition is part of the complete loop the fault current would travel. So we're accounting for this in our ZS readings or ZE. Um, while the path includes cables and connection resistance, a significant factor in the overall impedance comes from the inductive reactives of the transformer windings at the supply end of our circuit. So here's a nice little picture. So that's our supply transformer there. You can see the phase connected to the fuse and then the phase going to the inductive coil or the coil inside the toaster, which is then connected back to the neutral path. So when we talk about our earth fault loop impedance test, if we're measuring from the socket outlet that toaster is plugged into, we are measuring how much impedance would there be from that earth point back to the earth bar through our MEN link, down our neutral, all the way back to that transformer star point, and then through our windings of our transformer, back to our switchboard, through our fuse, and then to the phase outlet, sorry, the phase side of our plug. So it seems like a huge loop, but most of the time you'll come back in a residential setting with maybe 1.03 ohms. And I believe on a 16 amp 2.5 circuit, you can have up to 1.82. Don't quote me on that. I don't have the table in front of me, but it's something like that. And usually you don't get that. At a switchboard, the worst I've seen is 0.05. That was crazy high reading, but we had the right switch gear for it. Yep. Yeah. Yeah, you may not necessarily know the full EFLI circuit like I described, but you need to know that there's a transformer somewhere in the circuit at the supply side that produces reactance, and so we need to look at it as such. Is that the I'm sure that was that was the definition. Just making sure I didn't miss the slide. Cool. So yeah, so the main reason we do it, so the earth fault loop impedance test verifies that a sufficient fault current will flow to trip a circuit breaker or fuse in case of a fault, ensuring safety and preventing overheating or fires. So you guys remember when we looked at our circuit breakers, so we're checking to make sure the fault current will be high enough to trip that circuit breaker instantaneously. So usually at about 7 times its rating. So if you get a fault current of at least 200 amps and it's a 20 amp breaker, that's 10 times the current, you know it's going to trip it. We're also making sure it's not so high that our gear is going to break. So we have at the switchboard, if we have, say, 10,000 amps worth of fault current possibly, and we've only got a circuit breaker rated for 6,000 amps, we need to look at upsizing it. So they generally come in, the biggest I've used for domestic or like where people are living was 10 kA. But on the network, you'd be dealing with HRC fuses, which are like 80K plus. So that's be aware of that. Yeah, we need to verify that this fault current is going to be high enough and that we haven't overloaded our breakers with the prospective short circuit current. So the primary goal of an earth fault loop impedance test is to ensure that if a fault occurs in an electrical circuit, enough current will flow to operate the protective device quickly, preventing potential hazards. So the windings in the transformer form part of the fault loop, and because they are wound coils, they generate a magnetic field when current flows through them. So in the event of a fault, the sudden surge of current and the frequency dependent nature of the magnetic field introduces inductive reactance into the loop. So that's why we need to be doing a fault loop test. We can measure it with resistance, and there are values in the 3000 for that just base resistance, but we can't take into account what condition the transformer's in, how big the transformer is it operating correctly? Because sometimes transformers they just kind of half crap out, or not even fully crap out. I've had a couple jobs where you go to the client's house because they're complaining they don't have power, and you measure the voltage at the switchboard, and well, you've got 120 volts. Oops. So yeah, in that case, you call Wellington Electricity for us in Wellington, or at least it was until recently, and then they're like, "Oh yeah, we're fixing it. Yeah, we know the transformer's buggered. We'll be there soon." It happens. So if you get a high earth fault loop, so when we talk about high earth fault loop, so if our earth fault loop is too high, so our resistance, because there's two readings you'll get with the fault loop. You'll get a impedance reading, which is measured in ohms, and then you'll get a prospective short circuit current or prospective fault current, which is measured in amps. If your fault current is too high, um, sometimes if your fault loop the current is going to be too high, you need to change your breakers. If your impedance is too high, it can be one of two things: your cable isn't big enough and there's too high resistance in the cable, or there was a issue recently where in Wellington, I think one of my coworkers found it, where the transformer wasn't earthed properly, there'd been an issue with the earth, what it had broken or something. So sometimes they need to fix the earthing at the transformer. Yeah, because I think a lot. Yeah, so yeah, in rural settings, because you'd be so far away, or it used to be a earth return path, sometimes that can be an issue. Um, it's hard times. People are stealing copper off the transformers. There's like they use about 3 or 4 earth stakes in one direction, and then at 180 degrees do 3 or 4 earth stakes the other way. And if the readings still aren't good enough, they'll put more in. They do have a set reading they have to achieve, but again, each situation is going to be different. But yeah, distance does play a role in it, as well as soil type. So if you've got really sandy soil and it's dry, it's not a very good conductor. Whereas if you've got kind of wet, uh, kind of just normal dirt or mud, it works better, which is actually why they used to put the earth stake outside the house where the garden tap was, because the idea was that you'd leave the garden tap on slightly and the water would continuously wet the ground, and so you'd have a better conductive path through the ground. So why is it important? So safety reasons. If the impedance is too high, fault current might not be strong enough to trip the protective device, leading to overheating, fires, or electric shocks. And compliance. So earth fault loop impedance testing is a mandatory part of the electrical installation testing to ensure compliance with relevant regulations and standards, which is usually your first port of call is Section 8 of ASNZS 3000, which is your verification. But depending on your situation, whether it be medical, high voltage, dual generation, there may be other requirements that you have to meet as part of that. All right. And we've got any more questions about fault loop? A couple ways you can do the test. So you can either hook it straight into a power point at a receptacle inside the house if you're doing the house testing. If you're doing it the main switchboard, you would clip your multi-function tester or your earth loop tester. You would clip onto the earth bar, the neutral bar, and you'd put your phase probe onto the incoming from the main switch and then push the test button, and that would give your fault loop impedance at the switchboard. And then you can test, you usually test at the end of every circuit, because that's where the impedance or resistance would be the highest. There are readings you have to meet, and then from there, if it's you need to adjust anything, you adjust things. But it is a requirement at the switchboard. But some people read 3000 as long as you have RCDs, it can fail and it's fine. But at the end of the day, your RCD is not going to protect against a dead short. If there's a fault in the toaster between phase and neutral, your RCD only protects against earth fault loop or earth leakage. Um, but yeah, if it can't protect too much against short circuits, but it's good to know that your circuit breaker is going to trip, just in case the RCD fails. Um, hate to promote them, but Master Electricians a few years ago put out a pretty good video on how to do the test. I might put the link when I put the recording up on YouTube. I'll link to that video. It's done by the ex-CEO Bernie, who now works for my old company. He's a really good guy, but he does a really good explanation. It is a bit out of date, and the New Zealand Inspectors Association is working on putting out some more training material, and I think ETCO might be looking at doing the same. But if you're unsure of how to do the test, the best place for you to ask is your tradesman. If you're unfamiliar with how to do anything, your tradesman is the one who should be showing you the test. Or worst case scenario, ask a linesman because they do it a lot more often than we normally do on a residential or commercial basis. Any other questions? Does that clear things up, Sean, or not quite? Sweet. Cool. Thanks, Sean. Um, cool. So moving to a bit of a summary. So if you haven't taken any screenshots or anything, this one and the next page. So we call it Earth fault loop because the transformer windings, like I said, which are inductive by nature, oppose fault current through reactance, not just the resistance. And it's the opposition part of the complete loop the fault current would travel. So we account for it in the ZS reading. So you'll hear, especially if you watch any UK Sparkies who like to put videos out there talking about ZS or ZE or ZL. Um, but yeah, it's basically, as far as my understanding, your ZE is your earth loop and your ZL is your line or just the phase and neutral, which sometimes the older meters will only do a ZL or what they call a no trip, but it doesn't actually test the earth. So instead of using the earth, it just does it to the phase and neutral. And although it's a valid test for the circuit breaker, it doesn't meet the requirement for the earth fault loop. So if you're doing it to an RCD circuit, it's fine because technically we don't need to do an earth loop impedance, technically. But I'm always of the opinion that we should try and get multifunction testers that will do it. So the newest, even the previous generation to the ones that just came out, Flukes and Megas, will do a no trip ZE. Along with Matrels, if anyone's got those, they will do a ZE, or ZRCD, which basically does it at such a low current that it won't trip the RCD, but will still give you an accurate reading. Cool, and that's just the second page. So in the event of a fault, the sudden surge of current and frequency dependent nature of the magnetic field, it introduces inductive reactance. So industry uses ZS, total system impedance. So the impedance of the system, that's what ZS stands for. So ZE is your earth, ZL is your line, but ZS is the total system impedance to verify safe disconnection times and fault protection. This concept explains why impedance testing gives higher values than just pure resistance measurements would. So if you were to just measure the resistance, you would get a lower reading. But because we're measuring inductance, it becomes higher. This is also why if anyone does any motor testing, when you test the windings, the readings don't quite match the power on the nameplate because of the inductive nature of the motor windings. And then, yeah, just a full representation of what the circuit would be. So you can put anything on into that circuit. It could be your tail rail, it could be the stove that you use to cook dinner on. Cool. So some examples. So we're working with AC circuit calculations. We need to be aware that Z will most likely be used in place of R, but if the calculation is a generic question, either of the two letters may be used. But if you come across calculations where you have to deal with impedance, they will mention Z. So AC circuit, the current I is a result of both resistance and reactance in a circuit that has voltage applied. So later on, we'll look into further and more detailed breakdown. This stage, simplified manner, Ohm's law, just a Z instead of an R. Cool. So we'll do one example. So simple Ohm's law refresher. Given voltage equals 240 and I is 5 amps, calculate Z. So voltage equals I times Z. We can rearrange that to get Z equals V divided by I, which is 240 divided by 5, which gives us 48 ohms. So simple, nice and easy Ohm's law calculation. Yeah, so this is the kind of more simple question you might get in your exam. So it's just, yep, they've given you the voltage and the current, and they want you to figure out the impedance. So they'll either say it's an AC or a DC circuit, and from there you'll be able to figure out your impedance. Cool. So make sure you keep the units clear and always assume values are given in RMS unless otherwise noted. So given X equals 30 ohms and R equals 12 ohms and V equals 125 volts, we'll find I. So the first thing we need to do is figure out our impedance. And we know from earlier that Z equals R squared plus X squared. It's not quite clear. There we go. So we have our 12 ohms and our 32 ohms from our resistance and our reactance respectively. And then from there, we can go to square root of 144 plus 900, which gives us square of 1044, which gives us an impedance of 32.31 ohms. So now that we've figured out our impedance, we can use this to figure out our current. So we take our Ohm's law, V equals I times Z. We rearrange so that we've got I as V divided by Z. 120 divided by 32.31 gives us a current of 3.71 amps. So those are the steps we go through to figure out if we've been given our reactance and our resistance and our voltage to find our current. You could also do the same thing with your reactance. If you were given your impedance and your resistance, you could use X squared equals Z squared minus R squared. It's just a rearranging of the formula for Pythagoras theorem. Cool. So here you go. I leave you guys to figure these ones out. So given X equals 30 ohms and R equals 12 ohms and V is 120 volts, find I. It was just the yeah, no. Something gone wrong there. Give me a moment. I wonder if it is. It looks like the rest were changed. Okay. Voltage equals 230. Current equals 10 amps. Calculate the impedance. I just want to take time to remind you guys that we do look at how often you guys do post in the chat. So even if everyone's already answered the question, just keep chucking them in. That way, when I go and mark you attended, they don't come back and say, oh, but they've coined the term ghosting, where you log on and don't. I've had guys who have kind of openly admitted to going to rugby practice. So they log on and they go to rugby practice, and then eventually they get caught out. So don't be that guy. Oh, so Z equals V divided by I, which equals 230 divided by 10, which gives us 23 ohms. Always remember to put your units, guys. So don't just put 23. Always put what the unit is, whether it's voltages or ohms, because if you just put 23 in some of the online material or the capstone, it may auto fail you if you don't put the correct unit or if it gives you a list of units. Cool. So if resistance is 6, reactance is 8, calculate the impedance. Oh, so you're getting there? So, yeah, Z equals square root of R squared plus X squared, which is 6 squared plus 8 squared, which is 36 and 64, giving 100. So square root of 100 is 10. Another way to figure these ones out, if you're ever given a Pythagoras question where they give you any multiple of 3, 4, 5. So, sorry, 6, 8, or 3, 4, 6, 8, 9, 12. If it's any multiple of 3 and 4, the other side will be a multiple of 5 because of the 3, 4, 5 rule. Basically, if you measure one side 3, one side 4, the hypotenuse will always be 5. So if you ever need to check something is square or at 90 degrees, you can use the 3, 4, 5 method. And if it doesn't come out square, you need to adjust. Just a little tidbit from the building industry. Cool. So the impedance equals 18. The current is 3.5. Calculate the voltage. Yeah. So V equals I times Z, which equals 3.5 times 18, which gives us 63 volts. Cool. So given our impedance is 13 ohms and our resistance is 5, calculate the reactance. Yeah, what you got there? So yeah, so our x is equal to z squared minus r squared, which is 13 squared minus 5 squared. So 169. It shouldn't say plus there. It should say minus 169 minus 25, which equals 144, which equals 12 ohms. And can't say it's my fault for the putting the plus instead of the minus. I screenshotted these out of the learning resource that we were given to show you guys. Cool. Cool. So last one. So given voltage is 120 and resistance is 9 and our reactance is 12, calculate the current. So this is going to be a two-step question. All good, Sasha. Good to know that you're doing the first step properly. Cool. So yeah, we'll go over the steps. So yeah, first step, figure out our impedance, which is r squared plus x squared, which is 9 squared plus 12 squared, which gives us 81 plus 144, or 225, which gives us 15 ohms of impedance. And then step 2, I is equal to V divided by Z. So remember that triangle with V on top and I and Z at the bottom. So we need to figure out voltage, we multiply. We need to figure out current or impedance, we divide voltage by the other one. And that gives us 120 divided by 15, which gives us 8 amps. So that is all of the slides for tonight. But again, I am paid till, well, for 3 hours. So I will stop the recording.